today is kind of continue our discussion of what we were doing last time, which was essentially setting up a kind of silly loop that just counted up numbers. And in particular, I want to kind of look at the structure, compare the structure of loops as we might do them in C, and then kind of how, almost like to make this sort of pseudocode cookbook of how to, roughly speaking, how you would construct a loop of various types in assembly. Okay, so for that, let me start a new file. And I'm going to go ahead and do this, a C file, and then we'll look at assembly later. Okay, so okay, so let's just set up sort of a simple little program. Okay, and let's write basically in C the three different kinds of looping structures that we could have. Okay, so what are those? We could have a for loop, a while loop, and then the do while loop. Okay, the for loop in some sense is a special case of a while loop, but um, it's so common to use that kind of construction that C sort of makes it, it elevates it to sort of a primitive type. Okay, so let's just start with the while loop. Okay, so the basic form of a while loop is this. Okay, so what is condition here? Condition is some sort of Boolean expression, okay, meaning it's a thing that evaluates to either true or false, and that's it, okay? And in fact, I can, we haven't actually used this before, but the data type, why is it squiggly underlined? Okay, I'm not sure why it's squiggly underlined, but there is also the Boolean data type in C, and I'm not sure why it's squiggly underlined. Let me double check that I'm not being a moron. Okay, where's my Safari window? Oh, I bet you it's on the other. Oh, yeah. Okay, sorry. To use bools, you have to include there, and that should remove the error. Yeah, there we go. Okay. Yeah, anyway, so you can have a Boolean variable just like you could have an integer or a float or whatever. And essentially, a Boolean is a single bit variable, and it's either 0 for false or 1 for true. That's it. Okay. So we have some sort of condition. Now, in a lot of the programs that we've been writing, or at least the ones in C, this condition was something that was relatively complex. Okay, so for example, in the Caesarean cipher thing that you guys did, you had a condition on some of the if statements that was if the character's ASCII value is between two things, right? So you had if it's less than this and greater than that, and both things had to be true. So that to evaluate whether or not that was true or false, you really had to do three Boolean checks. Is this less than that? Is this greater than that? And are both things true? So there was a logical and in there. Okay, okay, but whatever the condition is, you have to check whether or not it's true. Okay, and then you do stuff. Okay, now under what circumstances do you enter the loop body here? Only if the condition is true, right? If the condition is false, you don't even enter the loop body at all. Okay, so is the body of a while loop guaranteed to run at all? No, right? Because if the condition is false, it won't run at all. Done. Now contrast that with the do while loop, which is what? Oops. Um, sorry, it did a thing to me. Okay, so code snippet for a do while loop, right? What's going to go here? Well, I have to have some sort of condition, right? And I have to have some sort of code, all right? So the loop body, let's just make that do stuff again. And then let's just say while condition. Okay, so what's the difference in the construction of these two things? When the condition is checked, okay, so is a do while loop guaranteed to run at minimum once, okay, because the condition is not checked until after the loop body has executed. So the condition for the do while loop is essentially should I continue looping, whereas the condition for the while loop is should I start looping. Okay, and I don't know, like when you guys were in 111 doing Python, you probably did while loops more often. In fact, I don't think Python has a do while loop. Um, it doesn't have that as a primitive thing. Okay, and then finally, of course, is you have uh, the for loop, right? And we defined it something like this. Okay, and so what were the sort of primitive pieces of how we set it up? Well, we need a counting variable that needs to start at some value, okay, whatever that value is. I'm just picking 0 here for sake of demonstration. We need some sort of termination condition, which is that we want to terminate or we continue looping while it's still true that I is less than or equal to 5. Okay, so whatever that is. And then how are we changing or updating our counting variable each time we go through the loop? Okay, in most cases, how do you update your counting variable? You just add 1 to it each time. Okay, but it doesn't necessarily have to be +1 every time. And you know, it could be +2 every time, for example. Like let's say you wanted to just count up on evens instead of all of them. Python made this really nice because how would you do this sort of construction in Python? Um, if I wanted to count by ones, I would do that, right? But what does Python allow you to do? Yeah, I could do something like this, okay? Why did I put 6 there and not 5? Yeah, it's always less than 6, right? So if I want to be less than or equal to 5, I need to be less than 6. Um, and this is one thing about Python that's always irritated the bejesus out of me is 0 is included, but 6 is not. And it bothers me. Um, yeah, so whatever. But if you add the third thing there, so the 2, how is it going to count up this time? By 2s, okay? Um, yeah, so I don't know, maybe you want to count up by twos for some reason. Got me. Um, okay, so let me just delete the Python. We don't really need that. Okay, so what I want to do is kind of look at, for each of these sort of versions of a loop, how would we set that up in assembly? Okay, and essentially what we're doing here is kind of mimicking what a compiler would do when it generates assembly, right? So you give it C, it spits out assembly, and then that assembly gets assembled. Um, and so we just need some loops here. Okay, so what would be a good example of a while loop? Let's just make something up. Well, like let's say, okay, I'm just making up something stupid here, right? So what is this thing going to do? It's going to print something. Now, what is my intent here? It's going to only print, like, say, 10 times, but as it stands at this moment, how many times is it going to print? Forever, because, yeah, because I never updated the value of num sandwiches, okay? And so I should decrement num sandwiches, otherwise I'm going to be in an endless loop, okay? Okay, so what will happen here is this should print that sandwich was yummy 10 times as the num sandwiches variable counts down and eventually hits 0. Okay, good. It's like plus plus, but minus minus instead, right? It just subtracts one from the variable instead of adding one. And here, right, I structured it thinking of counting backwards instead of counting forwards, right? There's no reason I have to count up. I can count down just as easily. And I mean, a for loop, you can do that too, right? So essentially what I've built here is really kind of a for loop, right? Even though it doesn't really look like a for loop. Okay, so let's do, let's basically write a sort of equivalent assembly program that would implement this kind of loop structure. Okay, good? We? All right, so let's start a new file. Okay, and now we're in ASM, so I need a data section, I need a text section, I need global main, and I need main, and then what's the, and let me change the syntax highlighting. Okay, what's the very first thing that our program should have? Store pair, x29, x30, stack pointer, minus 16, exclamation mark. And then at the very end, we need to load pair, x29, x30, stack pointer, 16. And we need to move 0 to W0 and ret. Okay, so that's basically every program needs to have that. Okay, now the other thing we need, right, is the string that we're going to print, and so I need to put that in my data section. And let me call it sans string. Sans string is my string. It's a string coded in ASCII, and so why did I type ASCII Z? What's the Z stand for? It's a null terminated ASCII string. And then, of course, the data that's in that string is whatever. and that's the only variable I have at this moment. I could, if I wanted to, go ahead and define a numeric variable to be my counter, or I can just use a register for that. I'll just go ahead and use a register for it right this instant, just to simplify things. But yeah, okay. So in order to print the string at all, okay, so now I'm thinking about my loop body. Let's just worry about printing the string once. What do I have to do in order to print the string? So in C, how would I do this? I'd say something like printf, and then something like that, right? So I need the assembly equivalent of this. Okay, so sans string is really a pointer to the string. Yes? Okay, so I need to pass the printf function a pointer. In this case, this is the only thing I need to pass it because I'm only printing a single string. Okay, so where is sans string? It's someplace in memory, but where do we know what the actual location is? No. Okay, so how do I sort of figure out that thing? I need to load its address, and I'm going to put it in X0. Okay, and then the equals operator here is kind of like the ampersand operator in C, right? It's going to replace that with the actual location in memory, whatever it is. Okay, and why am I putting this in X0? I mean, I've got 32 registers to choose from, so why that one? Hmm? It's not the only one that prints, but when I pass parameters to functions, I have to pass them in an order, right? So like, let's say I wanted to print 7 numbers, right? Um, so let's say I had something like this. Okay, and I'll just say 4 for the sake of demonstration here. Let's say I wanted to print 4 numbers, okay? I would pass it like this. Right? That would be the C code that I would write there, right? I have to give it a format string, and I have to give it whatever data that I wanted to print, either numeric values or pointers to other strings or structs or whatever, okay? All right, so how many things am I passing printf with the version on line 15? Huh? 8? Okay, why 8? All right, so four integers or numbers, whatever. In this case, integers. Yeah. Okay, 4 integers, and I'm also passing it a format string. Okay, which is to say I'm really passing it the address of that format string. So that's 5 things. Yes. One format string address and 4 integers for a total of 5 things. Yes. Okay. So if I wanted to do this in assembly, the convention is address of format string in X0, num1 in X, well, it'd be W1 in this case, etc. Okay, you can pass at maximum 8 things to a function that corresponds to registers 0 through 7, okay, which are in Linux on ARM designated as the registers you use for parameter passing, okay? So like the convention here is, so how many registers do we have on this processor? 32, basically 31, right? A couple of them have sort of specialized purposes, but 20 something that we essentially can really make use of. Um, that's not a whole lot, right? Um, although in some sense it's also a lot, right? Um, it kind of reminds me of how many of you guys have read Gulliver's Travels? Huh? Yeah, yeah. So there's a scene where there's two characters, Dr. Pangloss and Martin, and one of them is sort of always an optimist, and the other one is always a pessimist. And there's something where they ask some other dude, like, how many something or another's are there? And he tells them, and then both characters reply, that's a lot. And it was just kind of funny, right? So it's either a lot like in a good way or a lot in a bad way. I don't know. So that's your hashtag liberal arts college moment for the morning. Yeah. Okay. So uh, because there's 20 something essentially registers that we can kind of make general purpose use of. Some of them have to have special uses, okay, and that depends on operating system and all kinds of other stuff. But because we're working with an operating system, okay, the operating system defines a convention as to how you use these registers, which ones you use for parameter passing, which ones are reserved for sort of special system use, and so on. Okay, Linux basically has that system established. And because we're running on a Linux system, we had better observe it. Okay, now, if we were to sit down and write our own operating system, which we theoretically could, right? We could do whatever convention we wanted, but we would have to make up our own convention because otherwise it's just going to be a jumbled freaking mess and we'll drive ourselves insane. Okay? Um, so, thou shalt respect the Linux parameter passing conventions. And those conventions are parameters get or addresses of parameters get passed in the first 8 registers, 0 through 7. Okay, and the order of them corresponds to the order of them that you might do in C. Okay, so in this printf thing, I have to pass 5 things to printf. Yes, address of a format string, and then 4 numbers. And those 4 numbers I need to pass in a particular order because I want them printed in that order. Okay, so what would be the order that I put these in registers? What goes in register 0? The format string's address. What goes in the next register? The first number, then the second, then the third, right? It goes in order, right? Wouldn't, I mean, it would be illogical to just do it in any old order, right? That's not going to work. Yes? Okay, so why is it that the format string's address goes in X0, but the numbers are going in W's? What's the difference between an X and a W? X registers hold 64 bits. W registers hold 32, okay? And let's be clear, could I put something in X0 and something else in W0? Why not? They do. W0 is a part of X0. It's the lower 32 bits. Okay, so think of it like, if you go to Home Depot, how many of you guys have bought paint buckets for like painting the bench or something, right? All right, so you go to Home Depot, you go to the paint bucket aisle, right? Because or wherever the paint buckets are stored, and you saw that how many types of paint buckets could you buy? Yeah, but there's essentially like 2 sizes of paint bucket, right? There's the big 5-gallon bucket, and then there's the smaller like 2-gallon bucket. Yeah? Okay, so think of the W registers as being like the 2-gallon buckets, but they really are sitting down in the bottom of the 5-gallon big bucket, right? They're not completely separate entities, they're just the smaller bucket inside the bigger bucket. Is that okay? Okay, So that's why I didn't use W0, because I've already used X0. I've already used the whole big bucket. I can't also use the small bucket that's inside it. Yeah? Okay. All right. So, yeah, I like buckets. They're nice. Yeah. I like the word bucket too. It's kind of just has a nice sound to it. Um, yeah. I also like the Home Depot buckets, the orange. Yeah. Huh? Oh, you went to Lowe's? Yeah, but then you got to drive half an hour to Brownsburg. Oh, okay. Well, or better yet, how many of you guys, your hometown or whatever, has a Menards? Menards. It's a hardware store. It's like Home Depot or Lowe's, but it's sort of a Midwestern chain, and you can save some big money, right? Yeah, Ace is a small. Like Menards is like on the order of Home Depot and Lowe's in terms of size. So, yeah. Okay. Anyway, so right. So the registers, think of them as the paint buckets. Yeah. And there's a completely separate set of paint buckets for floating point numbers, and we'll talk about all that later. Um, but right now we'll just be dealing with basically the integer buckets. Okay. All right. So why is it then that the address of the format string had to go into a big bucket, an X bucket? Okay. How much data do the X buckets hold? 64 bits. Okay. Addresses of format strings, or addresses of anything, are 64-bit numbers, right? It's a 64-bit memory architecture. So that's why it had to go into an X. Now, as for a W, why is it I put the numbers in W1 and so on rather than X1 and so on? Well, what kind of numbers am I working with here? Integers, which are by default 32-bit. I could have done 64-bit integers, right? But that's a different data type. It's a long int rather than an int. Yes? Okay, so that's the order that I would put them in. Okay, now in this case, am I printing any numbers? No. So I don't need to worry about what we just talked about. All I have to do is put the address of the format string in register 0, and then am I ready to actually call printf? Yep, we're ready to go. So what should I put right below it? I need to call the function printf. How do I do that? I need to branch and link, so BL. B stands for branch, that's kind of like a go-to, and L stands for link. Link has something to do with the breadcrumb thing that we talked about, and we'll talk about that in more detail later, okay, as to how the breadcrumb system actually works. But that calls the printf function, it will do its thing, and then the program will return to right here. Okay, good? All right, do you guys mind if I get rid of this pseudocode? Good? Okay. So that does the printing. And let's assemble it, make sure it runs, and that everything's good before we continue. Okay, good? Oops. All right, so I've got my source here, Control Ask 2. So I need to assemble it and output to an object file. Oh, yeah, okay. It likes there to be a blank line at the end. That's just, whatever. Okay, and then let's see, we need to link it. So we've got control ask2.o and output to control ask2 or executable, and then run it. Okay, that sandwich was yummy. Yay, it printed. Okay, good. Hmm? Okay, so we've printed it once, but what do we want to do now? We want to set it up to print 10 times, okay? And for sake of demonstration, if I want to print 10 times, I could start at 0 and count up to 9, or I could start at 9 or 10 or whatever and count down to 0. Does it really matter which one I do? No. But let's say that for some reason I also need to keep track of the number of sandwiches. Let me go ahead and just do the subtracting, starting at 10 and counting our way down. Seem reasonable? Okay. And we're also doing this as a while loop, right? So when are we checking the condition as to whether or not to loop? At the beginning, before we execute the loop body. Okay. Now, this is where the assembly and the C are a little different from each other. Okay. So let's go back to the assembly for a moment, or sorry, the C for a moment. What's my condition here? While num sandwiches is greater than 0. Okay. I'm actually going to write this backwards on the assembly. So the assembly condition that I'm going to check is whether or not to enter the loop. And so my check is going to jump me past the loop if the condition is not true. So I'm going to, instead of thinking of is num sandwiches greater than 0, I actually want to check if it's less than or equal to 0. Okay, so that's sort of logically backwards, but there's a good reason. Okay, I just have to kind of think differently. Okay, is that all right? Yeah. Okay, so I need to do, well, a couple of things. First off, I need to store my counting variable and I need to initialize it somewhere, right? So in C, you did this by defining a variable num sandwiches and saying it's equal to 0 or whatever, right? But I need to do something like that here, okay? So where should I put this counting variable? Where's sort of a safe place to put it and where's definitely not a safe place to put it? Huh? Yeah, okay. I can put it as a data thing, which will store it in memory, and then I can access it from memory as needed. Okay. Um, I'll do that second, okay, as sort of a modification. In the meantime, though, let's just use one of the registers for it. Now, which register should I use? Okay, so remember the cheat sheet? In fact, let me pull it back up. And I forgot to put this on Canvas, so I'm a horrible professor, and you guys should all leave scathing reviews on the Rate My Professor website. Huh? Just yak about it. Okay, yeah, that might get you more traction, right? Okay, let me switch over to my Mac, and I'll put this on. Okay, so the thing that I want to look at is this, okay? This is the convention for how the registers are allocated for various pieces of use, okay? And um, let's look at all of them. X0 through X7, arguments and return values. X8, indirect result. X9 through X15, temporary. X16 and 17, inner procedure called temporary. X18, platform defined use. So basically Linux uses that for some special reason. X19 through X28, temporary, must be preserved. Okay, what that means is a subroutine is obligated to preserve them. So let's say a subroutine uses those registers, it's obligated to restore them to what they were when it started, when it finishes. Okay, so it, like, think of these as kind of like tools in the toolbox. Some of the tools you're obligated to put back the way they were when you started, and other ones you can leave laying around on a counter. Okay. Um, Okay, so let's use some of these temporary registers just for now. And so, well, let's use X19. It's the first one. Okay. All right. Is that okay? And then, yes? Good so far? All right. So let's go back to the pie. And let's put our counting variable in x19. Okay, so x19, I need to put I wanted to do 10. Okay, now this is something that's going to drive you guys crazy, which is the difference between LDR and move. Okay, essentially, the right, you think those are the same instructions. Okay, so if I want to put a specific number into a register or move data from one register to another, I'm going to use a move instruction. If I want to load data from memory, then I use an LDR instruction. Okay. Yes. Yes, because it's in memory, right? Um, and now I'm not actually loading the string into the register, I'm loading its address. So this LDR X0 with the equal is actually a shorthand for something a bit more complicated. We can talk about that later because we've still got tons to talk about in terms of memory and memory management. But yeah, essentially, if you want to put a specific value into a register, like a number of your choosing, we call these an immediate value, then you're going to be using a move instruction, not a load instruction. Okay. The pound sign after that is not necessary, but I find it's good to put it there just for, it reminds me that this is in fact an immediate number. Um, those things can be written in hex if you want. If you do not put 0x in front, it will assume it's base 10 and translate it accordingly. But there will be instances where we'll want to put in hex instead of decimal. So okay, great. And again, there's nothing special about the number 10 here. It's just I'm supposing we have 10 sandwiches. Okay. Now the other thing I need is I need the number -1, right? Or 1. And why do I need that number? Yeah, okay. When I increment or decrement, I need to add or subtract 1, okay? And there's a couple ways I could think about this. I could think about it as subtracting 1 each time, or I could think about it as adding -1 each time. They're equivalent, yes. Which one makes more sense to you? Adding -1? I'm seeing like disgusted faces up here in the peanut gallery, right? You think adding -1 is bonkers? Huh? Doesn't sound right. Well, you could do that to subtract 1. Okay. And actually, Jaden, we will look at the -1 situation. I'll do that a little bit later. But so for now, let's just subtract 1. Okay. The benefit of this is it means that we can talk about the subtraction operation, which we haven't used yet. Okay. Now, Jaden's point about adding -1. So those of you who were in 101, you guys remember the Berkshire architecture? Yeah. Was there a subtraction operation on that platform or that processor? No. And so I would have had to have added -1 instead of subtracting 1 because there was no subtraction. Okay. But here we do have a subtraction operation, so let's make use of it. So I'm going to put the number 1 in x20. Okay. Good. Okay. So then I need to have a check at some point here. Okay. But I also need to load, I really need 2 copies of the number 10. Okay. And the reason I need 2 copies is because one of them is going to stay as 10. Right. And the other one is going to decrement each time. Okay. So what am I checking? So like if I wrote this in C, I would have something like while num sandwiches is greater than 0 prints the thing, right? So this 0, I would need to store a 0 someplace for sake of comparison later. Or I could say, um, it this way. No, sorry, I want 10 minus num sandwiches. Right, I could also say it that way. Take the quantity 10 minus the number of sandwiches, and if that number is positive, then I still have sandwiches left. Right? It's a different way of saying the same thing. Yes? Okay, so let me do, let me actually put 0 here. And let me get rid of that for cleanliness. Okay, so I need to do my condition checking here, right? Which is I need to say, is the number of sandwiches less than or equal to 0? If so, stop looping. Okay? Or I could say, is the number of sandwiches greater than 0? Then continue looping. Let's do it the second way, because how would I write the loop in C? Well, how did we write it in C? Num sandwiches greater than 0. Okay, so let me show you how we would do it and keep that exact same structure. And I think you guys will see why it's actually going to be better to think backwards about it. Okay, so num sandwiches is being stored where? The number of sandwiches is being stored in register X19, okay? And the value that I want to compare it against is being stored in register 21, okay? So I need to do a comparison here. I need to do a comparison of X19 to X21, okay? Now, what does this comparison actually do, okay? What is, like, I wrote compare here, right? But what does that really do? It does the following. So let me go back over to my cheat sheet. Okay, and find where it does the comparison. Where do we have it? Here it is. Okay. Okay, so compare, I specify either two registers or a register and an immediate. So in this case, I could actually compare directly to the number 0 instead of comparing it to a register that has the value of 0 in it. Both are valid, okay? But what's the syntax of this? Who do I put first? A register. And who do I put second? Either of an immediate value or another register, okay? What actually gets computed here is the first thing minus the second thing, okay? So when I type compare, it's not actually compare. It's really doing a subtraction, okay? And what is it doing with the result of that subtraction? It's throwing that information away, okay? But this S over here in this column, what that does is this operation sets a flag, okay? So remember last time we talked about there are basically 4 integer flags: 0, carry, overflow, and negative, yes? So if I subtract, well, in this case, let's say I subtract 10 minus 0, okay? What flags are going to get set? Is the negative flag going to get set? Is the result of that operation a negative number? No. Is the overflow or carry flag going to get set? No. Is the 0 flag going to get set? No. Okay. Um, okay. So, right. So that's really what it's going to do is it does a subtraction and then sets the flags. Okay. So what do I follow a comparison instruction immediately by? Make a comparison, and then I do a conditional jump expression, which would be one of these. Okay, branch on condition. Okay, so branch if less than or equal to, right? So when do we want to, or greater than, right? So when do we want, what do we want our branch to do here? Do we want to enter the loop if the number is a positive number, which is to say it's not negative or 0? Yes, okay. So I want to branch on greater than here, okay? And that makes sense, right? Because how did I have the branch in C? Oops, this mouse. Yeah, I wrote it as greater than 0, okay? And we're trying to mimic that. All right, so I do a comparison. And then a branch. Okay, and my branch here is going to be branch on greater than or equal, or sorry, just greater than, because I wanted greater than 0, yes? Now, where am I going to branch? Let me call this loop body, just for shorthand. And what is my loop body? It's these two lines here, yes? So, when I hit this line, I'm going to ask, is it the case that I want to jump to the loop body? Yes or no? Right? Like, that's the question, right? And if I do, that's like entering the loop, and so I should go and start executing code here, okay? If I don't, then I want to go to whatever's after the loop, and I need to put a label there, so let me call this finish, okay? And there, I will make an unconditional jump to finish, okay? All right, so if my counter is greater than 0, then jump and do the loop body stuff. Otherwise, go to the finish and terminate the program. Okay, there's two things I need to add. Well, three things I need to add. Okay, what do I currently not have in my loop body? Do I ever change the counting variable? So I need to do that, right? Where am I storing my counting variable? X19. And where am I storing the number 1, the thing I'm going to decrement by? X20, okay? So I need to do a subtraction operation, yes? Okay, so I need to subtract what from what? I need to subtract X20 from X19, and where do I put the result? X19, okay? Because where did I put the number 10 that I was going to count down from? In 19, okay? So the order here is important, but what's basically the case is the destination is always specified first, right? So this is going to do the operation. It's going to compute X19 minus X20 and put the result in X19. Okay, is that all right? Yeah? Okay, so that updates my counting variable. That's good because then otherwise we'd be in an endless loop kind of situation. Okay, but when the loop finishes, what do I need to do? Okay, so as the code looks right now, what would happen after this operation on line 21 completes? It would go to finish and then here. Okay, so it is going to execute the next line of code sequentially. Do I want it to do that? No. What do I want to do? I want to go back up and do the comparison. Yes? Okay, so what I need to do is I need to have something on line 22 that takes me back up to line 14. Okay, and how can I do that? I need to do a branch, and I need to also put a label here so I know where I'm branching to. So let me call this check, because that's where we're doing a condition check. And then here, I would want B check. So that will take me back up to check. Now that I've updated the number of sandwiches, should I print something again or not? Okay, so so those are the three things that I needed to fix. Okay, questions before we try assembling it and testing it? Yes? Good? Ready to try it out? All right. All right, so let's assemble it. And I'm going to put all of this in one line. Okay, so that assembled it, linked it, and executed it all in one with a single line of terminal commands. And let's just count to make sure that we didn't F something up here. Did it print, in fact, 10 times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 sandwiches. Excellent. Were they yummy sandwiches? Yeah? Yeah. You'd like to have 10 sandwiches? Or 10 chocolate sundaes? No? That's a Star Trek joke. It's a kind of really obscure one, but yeah. Anyway. Okay, so 10 sandwiches, great. All right, let's look back at the code. And again, let's just make sure that we've got all the pieces under control here. Before we start messing with it. Okay, so any questions or observations about like maybe things we could change? Okay, with the one exception being Jaden suggesting of or adding -1 instead of subtracting 1. We'll deal with the -1 situation later. Huh? Yeah, where we store the counting variables and also the value that I'm adding or subtracting each time. Okay, I could have put those in memory someplace and accessed them from memory and updated their values in memory. What's one benefit of keeping them within a register and never having them have to go out into memory? So it's a benefit of that. There's plenty of drawbacks too. Well, one benefit is it's fast, right? Because if I started to put them out into memory and access them from memory, what is that? That's slow, okay, in comparison to working with registers. So think of memory access on a modern processor. There's really a hierarchy of memory, okay? Registers are sort of the ultimate form of memory. They're the fastest access, but you have the fewest of them. You only got 32 of the dang things. Okay, now processors nowadays also have other kinds of memory that are built on board. Has anybody built a computer in the last, say, year or so? No? Yes? All right, well, let's just take an example of, so I built a system in May, and, well, let's not look at the Jabberwocky. I used this processor for my build. Okay, 12600K, 6 performance, 4 efficiency cores at whatever thing. But in particular, what do processors have in terms of memory on board? They have this stuff called cache, okay? And notice it's only a few megabytes worth of stuff, right? That's oodles less than the amount of memory that's in the main system, which is, in the case of the system I built, 64 gigabytes. Okay, so this is a huge, like 2 orders of magnitude difference. Okay, but every processor has a little bit of memory sort of built into it, and that memory is faster than main memory, but slower than registers. And in fact, most processors have 3 levels of cache, L1, L2, and L3, with varying amounts and speeds of access again, okay? So we could store this stuff in memory, right? And there are going to be plenty of instances when we need to store stuff into memory. In this case, though, it was sufficient to store it in a register for just this silly little program. Okay. The other thing we could do is let's change the comparison here, because what I could have done is done a comparison to an immediate. And that would have done that subtraction right there. Okay. And then are we actually using register X21 in any way? No. So I can delete this because I'm not using it. All right, let's run that and make sure that it does the exact same thing. And let me scoot this up a bit so we can count that we have in fact eaten 10 sandwiches. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sandwiches. Okay. So I could have done that. The other thing I want to change, though, is I want to think backwards about the condition. Okay, and in particular, you see how I have 2 pieces of code here for branching? This one that says enter the loop body, and this one that says skip past the loop. What about if I replaced those with the following? Oops. So what about if I replaced those 2 with that single instruction? Okay, so what I want to think about here is not whether or not I enter the loop, but whether or not I skip past the loop. And then if I don't skip past the loop, then by default, what am I going to do? Go into the loop, because what is the instruction immediately after this instruction? The stuff that's in the loop, right? So by thinking of the condition backwards than the way I wrote it in C, I have made one instruction, been able to get rid of a single instruction. Okay, is that a good thing? Why? Why is this maybe a good thing? Why is one instruction better than 2 if you can do it? Yeah, speed, really, right? It's also less code and therefore less memory. I mean, 1 instruction versus 2 is not like earth-shattering savings, okay? But it is in fact slightly more efficient. Okay, which way do you guys like better? I mean, both are valid. No? Hmm? Which one would you rather do? The faster one, or the one that more closely resembles the order in C? Okay, so GTB finish, that's more like how the C code looks. Okay, yeah, so I mean, it's your choice, right? But you need to think very carefully about the conditions and the branching and stuff, because what can happen, and since none of you guys really programmed a whole lot of basic when you were younger, um, what can happen if you're sloppy when you do this, or you're writing a big program and you're not careful about this, is you end up with what we call spaghetti code. Okay, now I love spaghetti. It's very tasty, right? But what happens when you got a plate full of spaghetti? Yes, exactly. It's all, the noodles are all twisted up and stuff. And if you try and follow one noodle, you're going to get lost. Okay, so maybe an equivalent and perhaps a bit more reasonable of a statement would be, um, if you're not careful with your code, you're going to end up with something that looks like this, right? My mess of tangled wires, right? I mean, you guys have all had this experience. You're hooking up a bunch of stuff to a TV. You got your Xbox. Well, the Xbox needs power and it needs network, and you got to have an HDMI cable over to the speakers or the stereo system, and then that's got to have a cord that goes to the TV, and the TV also needs power, and maybe it needs network, and then somebody throws in a Nintendo Switch and a PlayStation and a Blu-ray player, and oh, then your jerk face professor is making you use Raspberry Pis, and so somebody needs to hook one of those up. And before you know it, what do you end up with? This, right? The rat's nest of cable. Okay, so when you're setting these things up, right, like here, we just wrote this program. All it did was print a stupid little statement 10 times. Did it do any interesting math? Did it, like, right? This was just a simple little program, and already it was pretty complex in terms of, we needed how many labels to do the job? Three. Okay, so I guess what I'm trying to say is, be careful and think very, very carefully about the structure, because otherwise you will drive yourself insane with this. You're going to end up with spaghetti code. Okay, so think carefully. Um, and if you can think in ways that reduce the number of instructions, that might make your life easier, but it also has a higher cognitive load. Okay. Um, yeah. Because what I don't want you, like, okay, we've used C as kind of a glue or a stepping stone into this assembly world, right? And just because it looks a particular way in C, as we've seen with this branching example, doesn't mean that that's the best way to do it in assembly. Okay, or the most logical or easy to conceive of way to do it in assembly. Okay, so using C as sort of a translational bridge is useful to an extent. If you go too far with that, then that's bad. Okay. Okay. Now, the other thing that you are hereby verboten to do, okay, would be, how could I have done this in another way that would have produced assembly that does my stupid little program without me having to write a single line of assembly? Yeah, I could use the compiler and tell it to spit out the assembly file instead of just writing it myself. Okay, let's do that. So it can be useful in terms of learning, right? All right, so let me get rid of the do while and the for loop out of this, just to make sure that my all right, so I've got my C file. Oops, let's go back here. All right, so let's do GCC control as2.c, and I want to output to control as2c version, that executable. Same thing, right? Well, I can do this. I can do GCC control as2.c dash s dash o control as to dot, not ASM, but just dot S. Okay, and that generates this. Okay, and in fact, let me put it side by side with um, with our assembly code, and let me get rid of the terminal just so we have some space. I would like for you to gaze upon those two things. And what do you see? They're very different. Okay. In what ways are they different? In what ways are they similar? Can you see the different structures that we used? Yeah, you can see branching. You can also see some moving of numbers like 10 to different places. You can see a subtraction. You can also see there's a comparison and a branch, right? And in fact, how did it structure the branching? It did it the first way, right? Because that's what our C code looked like, right? But what do you see the difference between this and these two things? It's very clear that one of them was machine produced, yes? Okay, so using machine produced assembly can be helpful to kind of see um, how a compiler does something and give you hints as to how to proceed or how to think about something. Um, but what would be bad? Yeah, if you turn that in, that's bad. Okay. Okay, so that's kind of like how many of you guys are in a foreign language class this semester? Which one? Chinese. Okay, that's bold. Yeah. Spanish. Okay. But have you ever used Google Translate to translate something into Spanish?
I use it for like individual words if I need help, but
Okay.
I've never turned something in and just directly translate.
Yeah. Using it for vocabulary or very short phrases like how do you say, excuse me, where is the bathroom, right? Or something like that can be useful, right? It's a perfectly good tool. Okay. But what happens if you take, like, you have to write a paper about what you thought about Don Quixote and you have to write said paper in Spanish? Okay. What would be a very bad approach to this? Write the paper in English, Google Translate it, and turn in the resulting Spanish, right? Because what kind of quality of Spanish are you going to end up with? It's going to be muy mal, okay? Yes, muy mal. And in particular, it's going to be very obvious that you've done so. But more importantly, I mean, so forget sort of the academic honesty or dishonesty angle here. What really do you lose out on if you just have Google Translate do it? Yeah, you lose out on the learning of Spanish, right? And guess what? How do you learn Spanish? By speaking it and writing it and reading it and listening to it, right? There is no substitute for doing it your damn self. Same thing here, okay? Google Translate can be a useful aid when you're learning languages, particularly for short phrases or vocabulary or weird idiomatic expressions that like so things where it doesn't seem that the phrase means what it means, but it does because that's just the idiom, right? It's kind of like in English, right? In a pickle. What does it mean to be in a pickle? Yeah, you're in trouble, right? You're in a not so great situation. But if you were somebody learning English for the first time and you came across this phrase, "You're in a pickle," you could read that and be like, wait, what? How do you fit into a pickle? What is a pickle, and how do you get into one? Right? This doesn't make any sense, right? So for understanding idiomatic expressions or vocabulary, or a range of vocabulary, uh, machines, references like that are extremely useful. Okay, and that is still the case about machine produced assembly, right? So I've learned quite a bit about assembly by looking at how machine-produced assembly would do something, okay? But it's no substitute for just writing assembly, okay? That's my moral of the story, okay? Okay, so let's just kind of recap before we quit, right? In order to set up a loop, notice that we've also had to use conditionals, okay? Because every loop has to have a conditional, right? Or possibly even multiple conditionals, depending on what you're doing. So where we're kind of going with this stuff, not right this instance, but for example, the Caesarean cipher program, you guys wrote that in C. Eventually, you'll be able to do the whole thing in assembly, okay, instead of in C, right? Now, when we get to that one, it will be slightly, like in one respect, it'll be slightly easier than doing it the first time because you already have figured out the math for what you need to subtract and when you need to divide by 26 and all of that business, right? So the idea of how to do the Caesarean cipher, you already know. Implementing it in assembly is going to be the hard part, right? Okay. Right. So branching and um, looping is kind of the thing. And the one last set of instructions, or a couple of instructions that I wanted to point out because they are useful, okay, is, okay, there is also this pair of instructions, CBZ and CBNZ, okay? What do you think those stand for? Yeah. Well, look at the meaning. Okay, so keep talking. Not zero and zero. So this means compare and branch on non-zero or compare and branch on zero. So these instructions are nice because they're a single instruction that does a compare and a branch. But those are the only two that exist. And if you think about the programs you write, how often are you doing comparisons to being either zero or non-zero? Quite frequently, right? Or maybe you don't think you are, right? But let's take, for example, my sandwich number. Could I have compared and branched on zero or not zero, depending on which way I structure it? Yeah, because when do I want to stop printing about sandwiches? When the number of sandwiches hits zero, okay? So you do have those two instructions also. And then there's this, the two that are at the bottom there, test branch on non-zero and test branch on zero is how you do bit level testing. So for example, in binary, how do you know if an integer is odd or even? Yeah, the last bit. And if you want to know whether or not the integer is positive or negative, what can you do? Look at the very first bit. Okay, so and there are other instances where you might want to check the value of a specific bit of a number rather than the entire number, and that's the difference between the test and the compare. It's test is a bit level thing. We won't need that for a while, but we'll need it eventually. So, all right. Well, I will see you guys on Tuesday, and after I post some diabolically evil assignments to Canvas.